This is one part that we've been working a lot, and it's totally new if you were here last year. So you'll enjoy this. It's really nice.
So, good morning, everybody. This session will be dealing with the steps preliminary to running the systems. So, essentially, the preparation, their preparation. The preparation steps are mostly two. It's composed by the actual system preparation part, which means to take a system from the PDB database and then assign titration states to residues, flip the residues to optimize their hydrogen bonding network, add hydrogens, of course, and from there obtain a system which can be passed to the proper build phase, which means to create files which are executable by the simulation engine. These files can be either currently in the Amber or in the charm format. Why this? Because as you probably know, these two different file formats support different types of force fields and also these different types of molecules. For example, in charm, the support for lipids is very good. So if you're going to simulate a membrane embedded protein, perhaps that will be your choice. For Amber, they have different residues already parameterized, or you want to use, for example, antechamber, and that would be a reason to go for the Amber file format. The idea of the preparation step is to be whatever degree is possible, system independent, so software independent, and also reproducible. So one important part, probably most of you have already prepared system more or less manually. What we want to do is to provide functions that allow you to go from the PDB file, so from scratch in a sense, to the runnable system in a way which can be reproduced easily, like automatically, and if necessary, it could contain some degree of randomness. For example, if you want to start with several replicas of the system in which the ligand has been put in different places, then you can do that because, of course, in Python you are able to code this randomness and accommodate it in the function, as we are going to see very briefly. So the general overview of the building phases is this. We start from a PDB file taken straight out of the PDB databank, that we call it M1. We have already seen, thanks to Joao, how you do that. It's just creating a molecule object, passing as a string the name, the ID code of the PDB. Then there is this protein prepare function, which will be discussed later. Which inside contains calls which we don't deal with directly because it's all dealt automatically, to first the assigning of titration states, which is done by PROK 3.1, and then the optimization of the hydrogen bonding network and the protonation, which is done by the PDB2PQR software. From that, you get a protein which has complete residues, so to speak. So all the hydrogens are there, and so on. That is passed to the solvate function. The solvate function adds a box of explicit water, taking into account, of course, steric clashes. So there should be no conflicts. In solvate, you specify essentially what will be the final size of your simulation, because it will create an orthorhombic box. So that again will be a molecule object. So sorry, I forgot. From the protein prepare stage, you get another molecule object, HTML molecule object. From the solvate, you get another molecule object, in this case containing also explicit water. Then you go through either charm.build or amber.build functions, which again we are going to discuss. These two call either PSFGen or TLIP, so the native softwares which are used for the two file formats to generate a runnable topology, which here we call as M4. from the output of the build step, we get the molecule, okay, okay, we know that. But also we get files in the output directory. I'm sure you're familiar, for example, with the PRM top file for Amber or the PSF for Charm. They will be put in the disk and will be used by the running steps. So let's start. As before, we'll be running these very simple steps online. The very first thing we do is to import HTMD. That's done. So the very first part of these steps will be the actual, what we call protein preparation. Essentially, it includes the step of computing empirical pKa values for the residue, keeping into account the residue's local environment. This essentially means, like, if we assume that the bulk value for the pKa of residues, we may be making an error because it's not keeping into account the local environment of the folded structure. There is software like PropKa, which takes into account this environment to tell you what's the effective pKa is. And then you compare this pKa with the pH at which you are expecting to do the simulation. And from that, you decide whether each residue is going to be protonated or not. This is done automatically. So this part is taken care of by PropKa. Then comes PDP2PQR, which does a combinatorial optimization of the hydrogen bonding, keeping into account the protonation decided at the step before, and in particular decides for histidine whether it should be protonated at the delta or epsilon position, and in which orientation it should be. And in general, it flips aspartic acids, asparagines, and glutamines in order, again, to optimize the hydrogen bonding networks. So it does this in a combinatorial way because these residues must be optimized all together. Again, this get mentioned. So the other side chains will be optimized as well. For histidines, glutamines, and aspartic acids, the best placement for the hydrogen is chosen. And then finally, the water hydrogens are also optimized. For this combinatorial optimization within the PDP, it's done by PDP2PQR. For the description of the algorithm, I suggest that you go in their website, which has got a kind of flowchart which explains in which order these steps are done to. While pKa calculation done by PropK 3.1. Why do I point out the version number? Because the standard PDP2PQR includes PropK 3.0. 3.1 gives slightly different results and should be essentially the same results, at least for the sake of protonation, as Schrodinger's Maestro protein preparation wizard. So at least for protonation, you should get the same states. For what concerns the optimization of the hydrogen bonding network, that could be different. So these are the pKa values for titratable residues in bulk. So, for example, if we are at pH 7, you would use aspartic acid negatively charged, and so on, while histidine would be neutral, for example. This pKa value, as we said before, changed according to the local environment. The protonation step computes these values and sets the protonation state by renaming residues. So If from the PDB file, for example, all glutamic acids are named GLU, if the preparation step decides that instead the glutamic acid should be protonated, so neutral, then the residue is renamed as GLH. After the preparation step, not only the name will be changed, but also the actual hydrogen atom will be present in the correct location. This is mostly an internal convention, but it's a convention. So it's good, be good to know that if you want to skip the preparation step, for example, which you can do, you can still decide or set your protonation states by setting these residues names. For example, with the mutate function. Now, there are some limitations to be considered. The first one is that PDB to PQR most of the times gives you reasonable results. So if you open the structure and you consider whether the hydrogens are put in the optimal arrangement or flipping as you would have done manually, most of the times it's like that. Sometimes it's not. And this is not always easy to debug. And the reason is that the software does this combinatorial search and returns a solution which is consistent with its own internal restraints, which are essentially the absence of steric clashes. But it doesn't mean that it's the optimal one. So that's something which comes from the software. And so you are always free to flip these geometries manually in the later steps. By manually, I mean with Python code, if it's necessary. Another point is that when we compute pKa values, we use a software called K, which doesn't deal with lipids. In fact, I think from what I know, it's still an open problem. So how to assign pKa values in presence of the membrane when they are exposed, residues are exposed to the membrane. There is some heuristic inside the code, which doesn't really solve the problem, but at least gives you a warning, which you probably should consider. And another problem is, if we assign the protonation considering a structure which is going to undergo large structural changes, then you may be making wrong decisions. In traditional MD, when conformational changes were small, this was not a problem. But since we are going to go towards, for example, folding the whole proteins, this may become something to be considered. So you might, if you are expecting very large conformational changes, you may want to redo the protonation, for example, at least check whether they are transferable between structures. So let's go to Python code. The first step, so the preparation, is done by the function named protein prepare. It should be rather intuitive. You don't need to give all these arguments. You just give the input molecule, which is a molecule with a capital M object, which is then prepared. Arguments are used if you want to first change the pH value for the proton for the sake of deciding titration, being more verbose, return details. By default is false, but I recommend you to put it to true because it will return a table showing the decisions which have been made. This we are going to see in detail later. Then there is an option for hydrophobic thickness, which is related to the membrane problem that I told you before. If you know that the protein will be embedded into a membrane centered at 0, as it is usual, z equals 0, then you can put the thickness of your membrane, and it will give you warnings about that. And fold selection is used if you want to override some decisions on some residues. Well, protein prepare returns a molecule object, which you can visualize with the functions that we have seen before. the molecule object differs from the one that you have given it as an input because, as we have mentioned, residues will have been renamed to follow the internal conventions, the convention. Then coordinates have been changed, and so on, and atoms have been added, and so on. And, well, this is the help, which, as usual, you get if you type question mark or you use tab, the tab key on the input. It's a normal Python help, so to speak. As I mentioned, you are not forced to use protein prepare. You can, if you know already your protonation, you can just mutate your residues, calling them GLH or whatever. I mean, if you want to, for example, to protonate the glutamic acid, you mutate it to GLH, or you can edit the coordinates. You have questions so far? Yeah.
Is there a size limit to the molecule? Because very often it's large protein complexes. Some of those POP programs actually fail because of the size limit. Are you aware of the limit?
I think we have run all of the proteins of the PDB through protein prepare, and I think we have statistics on how many fail, and they are not many. So I'm surprised. But I cannot tell you an actual number for the limit in the size. I think most of them were fine. Yes.
Maybe it's related with sometimes bigger complexes that missing atoms, and for example, it fails because of when there are too many missing atoms. I don't know. Yes,
there is some heuristic. This is mostly related to how many heavy atoms are missing. There is some heuristic which, since the protein prepare tries to complete residues when atoms are missing, using some templates, so to speak, typical shapes, so to say. If too many atoms are missing, then at some point it will say, I'm not going on because it's questionable. That's not an actual limit, it's more an heuristic to avoid large errors, so to speak. But we can have a look if we have a concrete case, for sure. So, doing the basic operation is quite easy. I'm loading a trypsin molecule, which is 3PTB, and I'm just passing it to the protein prepare and getting, as a result, 3RYP underscore op, which will be again a molecule. This will take some time, and I hope we can scroll. Let's go through the output. It's a bit verbose. So we mostly care about warnings. First warning is the following residue has not been optimized CA. It's because this structure contains a calcium atom. Well, of course, there is not much to optimize there. Then there is a warning about Ben, which is the ligand. It's benzamidine. Again, these are not dealt with currently by protein prepare. Then we get the actual decision which have been made, a summary. The residues which are in a non-standard state, so to speak, are reported. For example, for histidine 40, we got that the optimal hydrogen network optimization is if it's protonated on the epsilon nitrogen. All this CYX means that these cysteines do not participate to a disulfide breach, while if they are CYS, we don't see them, they do. IHIP means histidine protonated twice, both epsilon and delta, and so on. Now there is some, oops, oh my god. Let's go. Okay. Can you read it? Okay, now, warning, Davios protonation state, the pKa of 3 residues is within 1 unit of pH 7. This should be rather obvious. The normal heuristic is to say whether a pKa a value is less than or more than pH. But of course that could be wrong, because it's not a sharp decision boundary. We know that if we are within 1 unit of the pH, then the probability could be like 10% or 90% of being in the other state. So one shouldn't take decision for those whose, for example, pKa is very close to 7 as golden. And there is not much currently that can be done if not giving more than giving a warning. Yes?
The values to the right, they're already the ones that throw pKa.
Yes, they are. pKa is running in the background, and those are, yes, the ones decided. We'll see soon how to read all of them. If we are curious, for example, we can visualize one residue, which could be the number 40, for which we are informed that it's epsilon protonated histidine. So I'm using this view functions, and oh,
I don't think you can zoom.
I have a mouse.
Yeah. Do you have one? Tony, Stefan is a
yes, I'm clicking everything, but
it's in front, yeah.
well, it's not the best thing. It disappeared, but well, you got a glimpse of it. It was just the local environment of residue 40, and well, you can check with your intuition if you think the decisions are right or wrong. So we mentioned the return details function or option. Sorry. If we set returns detail to true, then we should be prepared to retrieve a second return argument. This is a Python-specific possibility of returning more than one value. We get the optimized version and this object. Now I'm running it. We get the same output as before, but I'm also printing prep data. Prep data shows just a summary. Essentially, it says residue data about 290 residues. It says which residues have not been optimized. And then it says that there is a full table of data into a property which is .data. So I will go in prepdata.data to retrieve the full version of this table, which here I'm just seeing in a summary. And for curiosity, it is a pandas data frame. Essentially, it's an object which you can index easily, so you can query like a table in a database. If I print it, I get it in this shape. So I'm not going through all the columns because we can also save this as an Excel file. See, these are all the residues and all the decisions which have been taken, 290 by 17 columns. Since prepdata.data is this fancy pandas object, it has a function which is to Excel, if we want, to save it as an Excel report. And that's what I'm going to do. So I created a directory and I saved this as an Excel file. So I think I can go back to the directory. And now it's here. An Excel file, which I open. And so I get a more friendly view of the table that...
It's on that one, you have to move it. No? Oh no, it's on this one. Because you have two screens. Okay?
Yes.
You have to move it.
Scan.
Exactly. Yes.
Okay. So this is essentially all the information that the preparation step has generated. We have residue name, the original one, the residue ID, again from the PDB, insertion code, because remember that the actual identity of a residue is this triplet from the PDB standard. So some residues will have, I don't know if here there are, an insertion code that you have to consider when you do queries for residues. Chain, of course. Then the pKa value, where it has a meaning. The protonation state decided, according to the naming conventions that we have seen. The flipped column will tell you whether that residue has been flipped by 180 degrees. This is in Spanish because of the PC, but it's either true or false. Patches, well, it's obvious, we won't care. Buried is the percentage of the residue side chain which is not solvent exposed. So 100% would mean that it's in the hydrophobic core, more or less. 0% would mean that it's completely exposed. This is just approximate. It comes from pKa. It's an heuristic. That is just the Z coordinate. Membrane exposed, right now it's all 0 because it's not a membrane protein. We'll see later that it will have a value if it is if it's relevant. And then there are other technical information which probably you don't really need. It's essentially due to the interface, the conversion between pKa, PDB to PQR, and our molecules. You might be interested, for example, in atom types, things like atom names and things like this. See, atom name, so where the protonation occurs, and so on. Let's see. You get this for all residues and also for the terminals. So the N terminus and the C terminus, which have their own rules for protonation. So let's go back to the presentation. No, essentially this concludes the preparation step. Now, what happens in case of membrane proteins? From what I know, there is no software which predicts pKa values for this, but there is a very recent article by Teixeira in which they studied the pKa for the commonly charged residues, changing their Z position from the bulk to the membrane core. So this doesn't take into account the rest of the protein. It was just the residue themselves. So it's not something that I guess you can rely on for your decision, but it more or less gives the idea that negatively charged residues tend to increase their pKa, and positive ones tend to decrease that, which means that more or less the general trend will be towards neutral residues. That's not much we can, that protonation, the preparation step can do, but we can do this. For example, suppose that we prepare the new opioid receptor for DKL. We could follow these steps. First, we retrieve it. We retrieve it not from the PDB, because it doesn't have a membrane and it's not oriented, nor it has a placement towards the center of the membrane. We retrieve it from the OPM, which is the orientation of protein in membranes database. So there is a function here, which is HTMD UT-OPM, which you call with this with the ID code, and it will retrieve for you the molecule and also provide the thickness, which we print. But I'm going to execute all of this. Sorry, press F11. F11 to make it full screen. Yes. Okay, so what's happening? It retrieved the opioid receptor, the oriented one. So it's placed in a way that the membrane centered at Z equals 0 is properly aligned with the hydrophobic region. It also returns the thickness, the expected thickness of the membrane, again from the OPM metadata. Then I only keep the protein, and then I optimize it, passing the hydrophobic thickness as the thickness computed before, retrieved before, and saving the details in more data. This occurs, and it's what you see here. The only difference as before, except of course that the protein is different, is that here now you get a warning. Prediction for 34 residues may be incorrect because they are exposed to the membrane. There is an heuristic here, which means give a warning if the Z coordinate of the residue is within the expected membrane slab, and also if they are not buried, which means that they are exposed to the membrane. Here I'm also doing some easy processing. Since I've got this more data.data table, the same that you have seen before, I can access the membrane exposed property, which is true or false. So exposed res is an index essentially which says which residues are exposed. And then I can just, for example, print them. So this would print the data for the exposed residues. Or this would save them into the Excel file. And that's what we could look at if we wanted, and what we are going to do. Let's see if it's the right one. All of them should have membrane exposed true, and in fact it's true. Yes. So I just forget about all the other residues, and I also only get the ones which probably I will want to check manually. So this was an example of how this data table can be easily queried. So, questions so far? Yes?
In practice, if you've got a knowledge model on primary structure that's not no-game, no-play, so you just look at the most largest protein rather than a big fitness.
Sorry, say it again. If you have if it's not in the OPM.
Yeah. Would you just go for the most homologous protein and just take the thickness from that in practice?
Yes, probably yes. The thickness is not very critical at this step. It's just for the heuristic for the purpose of giving warnings. What's really probably slightly more important is that you get it in the correct Z position, but that's a problem of, a priori, so to speak. It's you have to do that on your homology model. You have to make sure that its hydrophobic region is centered at 0. That's something that has to be in your model.
Changui, I think, does it. It finds an orientation.
But they cannot be Changui, so you would probably want a line on.
There is the OPM server.
From
Yeah.
the
So just a line on the same structure.
Yes, or you feed it to the OPM server.
I cannot feed into the wheels.
No, you can. I mean,
It's proprietary, cannot go out.
okay, no, if it's in this case, sorry.
Okay.
But I would say take the most homologous one, and well, I don't think it's critical, so to speak.
Sorry, you say that these 34 you will manually check. Can you be a bit more like, what it means in this context? Manually, visually, or what?
I think visually. I would say, but I'm not sure because really it's something I wouldn't even know who to ask, is to check which residues are there and possibly, for example, see that plot that from that article that I've shown. Are we close or are we far from the pH? If there is a large gap, then it will be protonated, or if it's not, then it will be neutral, but I don't know.
If it's charged, I would look into it, for instance.
Yes.
If the heuristic has given you a charged non-buried residue in the hydrophobic part.
Yes.
Inside the membrane, that would be odd.
Yes.
Buried, yeah.
So this concludes the preparation part. Now we assume that we have a structure in which residues have been completed and renamed. Now it's the time of building. Building goes like this. Let me go again to the presentation mode. First thing well, that's a simple example. I take again trypsin. I remove the ligand because we'll deal later with ligands. This is the very basic use. Then I do the preparation step, protein prepare. Then I apply auto segment, which puts segment names automatically on the various chemical molecules, which we can execute this. There is nothing new. We get the same output from the preparation. We may only want to check whether
if you do control minus, then it will actually automatically fit it. Try to do that.
You can also click on the left side to
yeah, I wanted to make it area.
like scroll down.
Now, yes. Okay, so the new part is builder created segments between residue 16 to 14, etc. This is the protein itself, which is correct, and these are water molecules, so they can go in their own segments. So all of this work is done by auto segment. As an alternative, you could assign seg_id property to anything which is unique among the various segments, various molecules. So now we are at typ_seg. Oops. Now, as we were mentioning, we need to solvate it to put the explicit water molecules. typ_solvated would be solvate of typ segmented with some padding. Padding, of course, means how much space would you leave on all the sides of the structure in order to give enough buffer. In this case, 5 angstroms. And now let's build for the charm format. In this case, we want to use the char22 star force field. So we set the topology, the list of topologies to this string, and the list of parameters to this string. These are standard in charm. There is a function to tell you which are available. But
actually, those files are not standard. They are made by us. There is not an implementation of char22 star, which is the best charm force to protein in charm. But this is with Creston and others should be okay. I mean, Creston is using this, so it should be fine.
Okay, but it is distributed with the.
It's inside ACEMD, but it's not inside that.
Okay, so this means that we can run it. It doesn't work because I didn't execute the previous step, so solvate. This takes a while. So, no, it's very fast.
Small padding.
Yes. And now I can just do the build. This behind the scenes calls PSFGen, which is the well-known topology generator which comes with BMD. It detects hydrogen bonds and puts it into the PSFGen input file, so they are
disulfide bonds.
Yes, sorry, disulfide bonds, sorry. 6 disulfide bonds are added. This does the build. Then there are some warnings which come from PSFGen. These are usually safe to ignore. Then there is ionization, so it's neutralized. And and then other warnings which you can read, but essentially what you get is a molecule and the files. Finish building, which means success. We also do, with the same structure, a build for Amber. The syntax is quite similar. The only difference in this case is that recent Amber distributions require that you specifically choose parameters for the calcium atom. Since calcium is present in this structure, then we can, one looks in the internet and figures out that there are at least 3 choices. This should be sensible, as far as I know. So one sets these parameter files, params, and calls the Amber build function. Again, it's quite straightforward. You pass the solvated structure, you add parameters, which is only necessary in this case because of the calcium atom. If you didn't have the calcium, for example, you don't even need to pass any parameter. I think the default force field is used, which I guess is FF14. And then you specify an output directory as before, which I forgot to mention. Everything, all the prepared topologies go into the directory that you specify here. We are going to see it immediately. So let's build for Amber as well. Note that you don't need to install Amber tools yourself because it's distributed with Conda. So you will have, this will work even if you don't install Amber tools. You get again some warnings, which in this case are totally safe. We scroll down. Again, there is the detection of disulfide bonds. And then if we go really down, we get to the finished building message. Which means that now, from a single structure, we managed to build both an Amber and a charm format system. If we want to be sure, now we are going to list the files, for example, in the 3out charm directory. As you can see, these were generated by the charm build operation. What we really want are the RTF files.
Those are already parameters, right?
Yes, no, sorry. What we really want are the parameters, the structure.psf, and the accompanying structure.pdb. This will have to reach the simulation software, and then we will be able to simulate. Or we could have a look at the Amber structure and the Amber directory. Here, the important ones are the PRM top, which is the topology and parameters, CRD, which is the coordinates, which may not be necessary because we also have the PDB. So we have the PRM top and the accompanying PDB, and we can start the simulation. The other files are in temporary files, so to speak. So if everything goes well, we don't even look at them. If something goes wrong, for example, as you probably are familiar with the TLIP errors, for example, you can have a look at the log files, or you can edit or have a look at what's going on in tlip.in. So tlip.in was generated by the Amber build function and then fed it to tlip. If at some point you want to see what's going on behind the scenes, just have a look at tlip.in. So you have all the information, in a sense, it's transparent. And this concludes the easy case, so to speak. Yes, please.
Is there any function for putting caps in NC terminal?
Yes, the caps are by default put there. The acetylated and N-methylation by default occur. If you want to disable it, or even specifically for some segments you want to disable it, there are options. I think it's called add caps or something, but it's in the help. So it's controllable, definitely.
How about hydrogen? So, for example, the problem I had initially, which I will work on now, is if you don't have any hydrogens at all, then it gives you a problem. So it assumes that you will have
residue. But then if you add it, then it's of course it's fine. So what I'm trying to say is that sometimes it relies on certain naming, and it doesn't change the naming unless it adheres to Amber naming, or because if you take it from some other software, then they add their own names.
Yes, well, if you take it from some other software, I cannot assure you. But if you go through Protein Prepare, then the names of hydrogens are made standard.
Yeah.
Well, the thing is, I think, with the cupping. So there was a problem with Amber build that required the hydrogens in the cupping.
Exactly.
But Joe made a new version where it's not required anymore, so you can throw anything at the chemicals.
That was exactly the issue.
Okay.
It never ran through.
So
Cupping assumed that you had hydrogen, for example, on the nitrogen. So.
Yeah, in the new version, I don't know when.
Yeah, I still haven't pushed it, yes.
Yeah. We'll have the new version without the need for hydrogens.
Okay.
I want to add another thing that so ACEMD distributes what we believe are the best force field automatically. That can be a little bit behind the scene, for example. If there is a chamfer K at some point, the default will probably be chamfer K. Or if there have been 3 releases of chamfer P6, which are called all chamfer P6, and we just update the default to the latest one. And the same for Amber and so on. So to see which file you want to use, so you can use any file, so you could specify which file you use. And I'm going to use Amber 15 still, but we'll soon move to Amber 16, and Chamfer 6 from August or February. If you do amber.list file or cam.list file, it shows all the files which are embedded, which are available in the default location, so the build will look for those. If you have your own, you just specify the full path for all.
Okay. So we could go on slightly more complicated build cases. In particular, I would like to show you a case in which the ligand has to be arranged, and we arrange it in a parametric way, in a random way. So we build a system which has a ligand in a random position. This is, of course, very useful if you have to build many replicas, as you have, as I've said before. Let me go to another presentation, which was actually made by Stefan. Which is this one. So we'll be building trypsin, this time with benzamidine. Again, it's the 3-PTB molecule structure. This doesn't work because I should call import HTMD before.
It's at the top.
Yes. I import HTMD everything, and I set my preferred viewer as NGL, so the web-based one. Now, let's load the molecule from the PDB database. Let's remove benzamidine because we are going to deal with it separately. So, protein.remove of the rest name of the Ben. To prepare the protein, as we have seen before, I just overwrite the prot object because I only want to deal with the protein, with the prepared one. Then instead of using auto-segment, just for the sake of illustration, I set segments manually, so I know that protein should have the seg IDP, or I want to give it the seg IDP, and water I give it W, and calcium Ca. Now I center it. This is important because we are going to do geometric manipulation, and so I got a reference. The protein is now translated so that its center of mass is at the 0,0,0 coordinates. And now we deal with the ligand. We have extracted the ligand and saved it into this bentrip./benzamine.pdb. So I load it, I center it, and then I can visualize it. Now, the ligand is fine, is it at the origin? it has to be moved because now the protein is at the origin of space. The ligand is also at the origin, so of course it doesn't, this is not what we want. So first thing, we rotate the ligand, so we give it a random orientation. We use the rotate by method on the ligand molecule and pass as a rotation a random rotation matrix, which is obtained by the uniform random rotation function. So after we execute this, the ligand will be in a random orientation, still centered at the origin of space. Now we need to follow, to have a look at this picture. It is at 0. We want to make it, to displace it in a direction, in the z direction, for example, by a distance which is as large as the protein. So we are as far as possible, more or less at the diameter, a diameter far from the, or a radius far from the center of the protein. So we import the function max distance, and we compute d, which essentially will be the maximum distance of the atoms from the protein atom from the origin. We add some generous amount to d, so 38 angstroms, and now we move the ligand in the x direction by 38 angstroms. So we have a protein and the origin. We compute that the radius of the protein is 28 angstroms. We displace the ligand from the center to the x direction by 28 plus a buffer, so 38 angstroms. So now, to summarize, the ligand is outside of the protein in a random orientation at 38 angstroms of distance from the center. We execute it, we don't see anything because it's all done internally. The final step would be move it, do another random uniform rotation around the center of the space so that the protein, the ligand, instead of being on the x-axis, is somewhere around on the sphere around the protein, uniformly distributed. So I hope I explained myself. I try to say it again with my hands. Protein and ligand. Orientate the ligand in a random direction, displace it in the x direction, then rotate it around the origin of space in a uniformly random manner. This should put the ligand in a random orientation, in a random position on a sphere at 38 angstroms of distance from the center of the protein. Every time we execute this function, the results, of course, will be different. Now, we only need to set the segment for the ligand. We do it trivially. We set seg_id on ligand. For now, the molecules are still separate objects in memory. There is the trip and the ligand. And now we can combine them. So I create an empty molecule, like this, mol equals molecule. To the empty molecule, I add the protein. To the empty molecule, I add the ligand, the newly oriented ligand. And then I can visualize them, the representation properties. If we are lucky, we see that it occurred as we expected. See? Questions so far? Okay, now for now we only have the solute. We need to add the solvent.
Can I ask a question?
Yes.
So if you wanted to add multiple copies of ligands, would you just
Sorry, can you speak a little bit louder? Sorry, I can't hear you.
Sorry.
I can't hear you.
If you want to add multiple copies of ligands randomly, would you just do that in one shot? I guess there must be some comprehensive code you could just put in to do that. If I want 5 or 6 replicas of a ligand in a box,
Yes, if you want to have them in the same system, you can do that at the same time. There are several ways to do that. If there are not many, you just instantiate ligand 1 equals a molecule containing the ligand, and then you rotate it twice, as we have seen. Then you instantiate ligand 3 and so on. And then you add all of them to the combined molecule. That should simply work. If you think that you're going to have, for example, a variable number or really too many to code by hand, you can make a loop. It would work as expected, I would say.
Same way to take clashes. I mean, it might be very unfortunate and ligands on top of each other.
Yes, I guess probably in that case you would want to, for example, when you add the second ligand, you could use an option to the add method, to the append method, which says to avoid steric clashes. Essentially, it will not add the ligand if there are steric clashes. Or you can just do in your code a distance of computation, for example.
You should start there in append, so you see the append.
In append, yeah. There is an option.
Yes, so you can see the help. Right.
Add a few more times. Shift tab, shift tab.
Okay. I don't know if it's readable.
Yeah. You can even do one more, and it's gonna pop it up.
Okay, so the append function has got an option which is collisions equals false. So by default, it doesn't care if there are collisions, but if you set it to true, it will remove residues of the incoming molecule, or the one that you're adding, if they are in steric clash. So in this case, it wouldn't add a ligand which would be in clashing. Otherwise, perhaps I would just have a look to the distances, for example, with atom selections. Yeah, or compute in a loop distances from the center of mass or things like that. Now it's the solvation step. We recycle the buffer, the size, the molecular radius that we computed before. We add 5 angstroms, which means essentially 5 more angstroms in each direction of the box. We call the solvate operation method function, passing the min-max array, which means essentially the box size, and that should simply work. It works, but we don't see it.
Again.
With the bit of the viewer, you can also. So
Still working. We will see.
No, it's a visualization that takes a bit to the NGL viewer because it has so many water atoms. It's going to start. Just a bit. Yeah. There it is.
Okay, and that's what we expected. The same system as before, solvated. We could play with representations, of course, if we wanted to have a clear view, but you get the point. Now, it's time to do the build operation. As Gianni was mentioning before, we can have a list of available force field by using the chart.listFile function. This will tell us that we could use all of these pre-supplied force field. We decided to go again for the chart 22 star force field, but in this case we need the benzamidine parameters. They come from the parameterization step that will be shown by Matt later. So we assume to have them already, to have them in the Ben3 directory, and so we call the charm build method. As before, we pass it the solvated molecule as a first argument, then the list of topologies, so chart 22 star and benzamidine topologies, the list of parameter files, again, And then we tell it where to store the results, out 3B, out build. We do this, and after a while we get the structure prepared. And I guess we don't wait for it. It takes like 2 minutes, I guess, but at the end you get it and you can view it. So I'm not waiting because I'd like to go to the next tutorial.
Just press the X on the left.
Yes. So this tutorial has shown how to prepare, first of all, how to add a ligand, and also to introduce randomness in a sensible way, so that the system should be valid, random, but in any case valid when you run it. Let's go back to the directory and go for number 3C. This is instead building a system embedded in the membrane. In particular, it's the mu opioid receptor. As before, we execute the import ACEMD star. We visualize, we can visualize the structure. The structure comes from the OPM database. So if we get it straight from the OPM, it will have these fake dummy atoms, which have a residue name of DUM, which are placed at the predicted location of the two membrane slabs, beginning and end. We have to remove these dummy atoms to go on with the preparation step. And we do this as follows. I import the OPM function, then I retrieve for DKL with the convenience function OPM, as we have done before. I get the thickness back, and I note that OPM already removes the dummy atoms, so I can just use prot. It's ready to use. I think this structure is a dimer. I want, for the sake of speed, I only deal with a monomer, so I only select chain B. And I remove other stuff which I'm not interested in. So I use the filter function, and then I use the auto segment function, which correctly recognizes that there are just 2 segments. So it's due to the fact that there is a non-resolved stretch of protein. So 2 chemically connected segments. For building, we build the first the protein for now without any solvation. We need, since the protein has a ligand, we add the parameters for this ligand as before. And everything should go smooth. In fact, it's fast because there is no solvent. We can visualize the current status. And that's what we expected. Now, the structure has a sodium atom. We treat more or less as we did it with ligands. We retrieve it from the disk. It's called SOD. We set its segment, we append it to the protein, and we visualize it. You can see it in the middle. Now we leave the membrane. We load a membrane from the disk. This is a large stretch of membrane. I don't know if it was created by Charm GUI or perhaps by VMD, but in any case, on the web you can find pre-equilibrated membranes. They all work well. I center the membrane so that its center lies in the same place as the center of the protein. So P protein center is equal to the mean of the coordinates of the protein. So from the protein, I select the protein atom selection, I get the coordinates, which means essentially a large matrix of coordinates, 3 columns x, y, z, and as many rows as atoms are. Then I pass it to the mean numpy function, which computes the mean along atoms, so along the rows. So P center would be, let me execute this. P center would be a triplet, a vector of 3 coordinates, the center of the molecule. The same for the M center, which would be the center of the membrane. And then I move the membrane by the difference vector between protein center and membrane center. So I translate the membrane so that its center coincides with the center of the protein. Now I'll make a copy of the protein. I call it mol, and I append the membrane to it, making sure that there are no spherical clashes. So lipids which would be in clash with atoms in the protein are simply not appended. This is taken care of by the collision equal true, which we were mentioning before. Now, in mol, we have protein and membrane. We can now visualize it.
25 minutes, okay?
Yes, I'm finished. And as you can see, you have the membrane and the protein, sodium atom, and so on. We now add the ligand. It's in the directory more again, qm-minimize.pdb. We set its segment to L. We center it. We place it in a random position in the XY plane, which has a Z coordinate of 43. So essentially it's above the protein, above the membrane at a distance of 43 angstroms, in a position which is in the square minus 10 to 10, minus 10 to 10. Then the ligand itself is rotated around its center to give it a random orientation, and then moved in, I don't remember where, and then appended. Sorry, I compute the center where it is supposed to go, then I rotate it around its center, and then I move it to its final position, which is the one which I just computed. And then I append it to the molecule. And that's done. Now I solvate it. Note that I'm solvating after I put all the elements of the system, otherwise adding them would clash with water molecules. These two instructions are to compute a sensible water box, minimum and maximum, and then it's passed again to the solvate function. And we are done. So now, well, this is to visualize. We don't visualize. I guess we can trust it because it's a bit slow. And now we can do the build. The build just occurs as before. We build the solvated molecule. We use the topology and parameters that we decided before. We say store everything into this output directory, and this time we want to use a certain salt concentration. So ions will be added to get 150 millimolar ionic strength of I guess sodium and chloride, if I don't mistake, by default, and of course you can change them. This again takes like 2 minutes. We don't wait, but the point is that now we have got a fully built system. And essentially this concludes my presentation. After we have run all the tutorials, we have the output directories and we can browse in them. In this case, the output is not finished yet, but when it's finished, for example, in build, we get, as you can see, all the files required for the simulation, and also all those which have been used to prepare the system, for example, PSFGen input files. So that's essentially it.
Question?
And if you have questions, I'll be happy to answer.
Yeah. You center the molecule within in the membrane. What if the orientation is not the right one? How would you have that?
Do you mean the new opioid receptor?
No, the membrane protein.
Yeah.
The membrane protein is centered in the coordinates, but it could be in a different orientation. So that
we assume that when we download it from the OPM database, it's already in the correct orientation. In fact, the OPM database, it was made so that orientation are correct. It's orientation of protein in membrane. So the orientation will be the Z, assuming a membrane in the XY plane. So the proteins are rotated so that they are straight, so to speak. And also they are situated in the Z position in a way that the slab is centered in the hydrophobic region. It's orientation and depth, so to speak. That's why I'm using the OPM download function, not the generic PDB download function.
and how are the missing residues built?
If they are completely missing, they are not built. For example, if the carbon alpha is missing, no attempt is done. The segments are considered disconnected and they are cut. Say, for example, that 3 residues are missing or a loop is missing, then the N-terminal stretch is terminated by is cut. Then there is the missing part, and then there is the other cap and the rest of the C-terminal region. If you want to do loop modeling, then it's not covered by this tutorial. If heavy atoms are missing, but not carbon alphas, so if residues are incomplete, so to speak, then they are rebuilt. I think depending on heuristics, which take into account the curvature of the backbone. It's done either by a protein preparation or PSFGen or TDEEP. I guess all of them have some heuristic to reconstruct residues.
Okay. What's the start? Have you tried really using amber levels? What's the status of ACEMD with amber?
I think there is they are parts of the
So they are reconstructed from charm. So we have these two that so actually we use there's an amber tutorial on how to work with lipids in amber. I think it's the official one, and you just use the I don't know.
Yeah, in the official amber tutorial, it essentially says to take a charm membrane and convert it to the state that they have. So to an amber membrane. We do this internally, so you don't need to care about it. It's converted automatically from a charm membrane to a number.
So when so initially what was happening was I don't know. I mean, since then that when I built it externally, I wasn't able to simulate it in these some programs, and I was working with the plus forms. I don't know how they do it. So basically, just run exactly with amber and
if you have a memory with charm naming and stuff like that, it will be automatically converted to amber, and it will basically that's it. And all the
and at the
parameters
end,
will
you
be
just get a PRM file, and it should just simply
Yeah. Actually, that part is solved. That part works well. Yeah.
I think from what I know, one part is to rename charm atoms so that they match the names expected by amber. And then for the force field, the new amber force field for lipids is used. So it should be official, so to speak.
It seems that you're using rectangular boxes for everything. Is there any options to look at alternative shapes so that you might be able to reduce maximum?
No.
Okay.
It doesn't. We've never done that because he adds a bit of complexity in visualization and also running the code, and it doesn't actually run a lot faster by doing that. So maybe go 50%, 25% faster if you use the software for that. But remember broadening.
Yeah, I'm just looking at fragments if I've got with the actual GS underneath there, and I saw that in a rectangular box. It's like something ridiculous actually. It's quite a large system, and then if I use a smaller shape, I can get down by about 35%, which is quite positive.
Or what shape would you use for a number problem?
Yeah, because in that case you're thinking about the G protein underneath, right? But if you want to shape it around the box, it's not like it can be uneven. It has to be.
I would use as octahedral or something like this, but for a number problem, then you just really say very little between the corners. And of course, for a water-soluble protein, we say around 50%. But then the column is one below that thing, not off the force. And then you have this thing oddly in the screen that you tell that it's such a big thing.
You have a considerable for a long molecular
the bigger you go, that's 30%. The bigger you go, the longer it is. That's 30%. Okay. Another way to do that, which is more efficient, is to keep the protein in a certain orientation and so on. So that would actually save a lot compared to 50%. So if you have a protein which is more rectangular, soluble protein, and you want ligand binding, for instance, and you refrain the protein from rotational diffusion, you can have a smaller box, way smaller box, and it's way less than 50%. But if you something that I mentioned that really, if there are more questions, we have to go because the lunch is short.